This approximation appears to become better as n approaches infinity, and recognizing equation 3 as a Riemann sum for the function g of x equals 2 pi f of x times the square root of 1 plus open bracket f prime of x close bracket squared. We have the limit as n approaches infinity of the sum from I equals 1 to n of 2 pi f of x star sub I times the square root of 1 plus open bracket f prime of x star sub I close bracket squared times delta x equals the integral from a to b of 2 pi f of x times the square root of 1 plus open bracket f prime of x close bracket squared dx. Therefore, in the case where f is positive and has a continuous derivative, we define the surface area of the surface obtained by rotating the curve y equals f of x. A is less than or equal to x, and x is less than or equal to b about the x-axis. Equation 4, big S, is equals approximately, big S equals the integral from a to b times 2, restarting equation 4. Big S equals the integral from a to b, 2 pi f of x times the square root of 1 plus open bracket f prime of x close bracket squared dx. With the Leibniz notation for derivatives, this formula becomes equation 5, big S equals the integral from a to b of 2 pi y, the square root of 1 plus open dy over dx close squared dx. If the curve is described as x equals g of y, c is less than or equal to y, and y is less than or equal to d, then the formula for the surface area becomes equation 6. Big S equals the integral from c to d of 2 pi y times the square root of 1 plus dx over dy squared dy. And both formulas 5 and 6 can be summarized symbolically using the notation for arc length given in section 8.1. As equation 7, big S equals the integral of 2 pi y ds. For rotation about the y-axis, the surface area formula becomes equation 8, big S equals the integral of 2 pi x ds, where, as before, we can use either ds equals the square root of 1 plus open dy over dx close squared dx, or ds equals the square root of 1 plus open dx over dy close squared dy. These formulas can be remembered by thinking of 2 pi y or 2 pi x as the circumference of a circle traced out by the point open x and y close on the curve as it is rotated about the x-axis or y-axis respectively. See figure 5. Figure 5, equation A, figure A, rotation about the x-axis. Big S equals the integral of 2 pi y ds. The circumference is equal to 2 pi y. We have a distance y and a point x and y. And figure 5b, rotation about the y-axis. Big S equals the integral of 2 pi x ds, where the circumference is 2 pi x. We have a distance of x to a point of x and y. Back to the text. Example 1. I should see the curve first. Sidebar, figure 6. Figure 6 shows the portion of the sphere whose surface area is computed in example 1. We have 1 marked on the x-axis. Back to the text, example 1. The curve y equals the square root of 4 minus x squared, where negative 1 is less than or equal to x, and x is less than or equal to 1, is an arc of the circle x squared plus y squared equals 4. Find the area of the surface obtained by rotating this arc about the x-axis. The surface is a portion of a sphere of radius 2. See figure 6. Solution. We have dy over dx equals 1/2 open 4 minus x squared close to the power negative 1/2 open negative 2x closed equals negative x over the square root of 4 minus x squared. And so by formula 5, the surface area is big S equals the integral from negative 1 to 1 of 2 pi y times the square root of 1 plus open dy over dx closed squared dx equals 2 pi on the integral from negative 1 to 1 of the square root of 4 minus x squared times the square root of 1 plus x squared over 4 minus x squared dx equals 2 pi, the integral from negative 1 to 1, the square root of 4 minus x squared times the square root of 4 minus x squared plus x squared over 4 minus x squared dx equals 2 pi, the integral from negative 1 to 1, the square root of 4 minus x squared times 2 over the square root of 4 minus x squared dx equals 4 pi, the integral from negative 1 to 1 of 1 dx equals 4 pi of 2 equals 8 pi.